Okay, guys, so let's talk about stoichiometry. We've taken a couple of days and gone through the mechanics of it. Now let's go through the rest of our lecture. Hopefully we'll finish this today. If not, we'll be very close. So here's our balanced equation, and our question is what mass of phosphorus? So that's what we want to find. So we want to find how much P, and will be needed to produce 3.25 moles of P4O10. So what kind of conversion factors are we going to need? Well, we're going to need a conversion factor that 1 mole of P4O10 is 4 moles of P. And you see I've lined that up so that the moles of P4O10 cancel. And then the molar mass of phosphorus. Our starting number had 3 significant figures. So our answer also has 3 significant figures, and the 0 in between the 4 and the 3 is a captured 0, so it is significant. We have rounded to 3 significant figures. So yes, significant figures are coming back. So what's the general procedure? So you're given a quantity and you have to look at that unit. And then you're going to identify what you want to find and identify that unit. You're going to need a mole-to-mole ratio from the balanced chemical equation. And then you're going to need whatever other conversion factors you need to go from what given unit you have to moles, and then from moles of what you want to find to the unit you want to find. And so, if we have molar mass as one of our conversion factors, we would, if we're given grams of a starting material, we would need 1 mole over the molar mass of that substance. If we're trying to find the mass of something being produced or needed, we would have molar mass divided by 1 mole. So you would use the one on the left with your given, and you would use the one on the right with what you want to find. The other couple of places we could start or end would be particles or liters of a gas at STP. And again, there are 2 conversion factors. One, we would use the 2 on the left, we would use with our given, and the 2 on the right, we would use with what we want to find. So here's the same sort of chart I gave you, but written out maybe a little bit differently. And if you like doing this, that's fine. Just remember, whatever you want to find does not have to be a product. It could be a reactant. This at the top is not a balanced chemical equation. It's just showing the relationship between what you're given, where you're starting, and where you want to end up. So, how do you think manufacturers of airbags know how to get the right amount of air in an inflated airbag? And it's not really air in an inflated airbag, but it's close. And basically, they use stoichiometry and they use STP to calculate how many grams of a material they need to put in the bag that will then inflate to give the airbag its particular volume that they want. So, I'm going to go through a couple of problems now, and these are also in your book, but I'd like you to attempt to work them out. So I would like you to pause at this point, or actually maybe after the next slide or two, and then you can work it out and see if you get the same answer I do, or that they do. So how many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis according to the balanced equation below? So we are given that we have 29.2 grams of water. We want to find molecules of O2. So our plan is to go from grams of water to moles of water. And that one I would use the molar mass of water. To go from moles of water to moles of oxygen, you're going to use the ratio shown below from the balanced chemical equation. And lastly, to get from moles of oxygen to molecules of oxygen, you are going to need Avogadro's number. So here's the various conversions you need and your known and unknown. Go ahead and pause here and see if you can work through to the answer. Okay, I'm going to go on. So when we line this up, we want to make sure our units cancel. So since we have grams of water here, we're going to have to put grams of our molar mass on the bottom and 1 mole of water on the top. Now that I have 1 mole of water on the top, I know my 2 moles of water go below on this line, and then 1 mole of oxygen goes on top, and then 1 mole of oxygen in the denominator, and then Avogadro's number in the numerator. Each one of these is identified as to what we're trying to do. And then lastly, we get this answer. And again, you're definitely going to want to use scientific notation for this. And if you're to write this out for me on maybe eLocker, where you can't do superscripts, you can use the little caret looking thing up above the 6 as your indication that that's an exponent. Here's another example. Nitrogen monoxide and oxygen gas combine to form brown gas nitrogen dioxide, which contributes to photochemical smog. How many liters of nitrogen dioxide are produced when 34 liters of oxygen react with an excess of nitrogen monoxide? Assume conditions are at STP. You notice they're saying you're not worried about how much oxygen you have plenty. And so we're only interested in the relationship between NO and NO2. So what are we given? We're given 34 liters of O2. How many significant figures does that have? Pretty easy to see. It's just 2. And we have 1 mole of O2 is 22.4 liters, and 1 mole of NO2 is 22.4 liters. And the volume of NO2 is what we want to find. This one is kind of actually simple because a lot of things cancel out. In fact, I would put a line through the 22.4 here and the 22.4 here. And then you're just taking this and multiplying it by 2. So pretty straightforward.